So let's look at how statistics help civil engineers extract meaning from messy real world data. Whether you're assessing infrastructure health, modeling delays, or improving designs, statistical tools let you make data driven decisions under uncertainty. So, what is statistical analysis? It is the process of collecting, analyzing, interpreting, and then presenting the data you have. In civil engineering systems, we use it to find patterns, estimate performance, or highlight risks, like predicting failure times or evaluating traffic flow changes after a policy shift. There are three main types of statistical analysis. Descriptive statistics help us summarize the data we already have. We can take a very, very big data set and divide it into some key elements and then understand them and comprehend them. And they would give us the bigger picture, although they're fewer in number. Inferential statistics lets us make predictions and decisions about a larger population based on a sample of the bigger population. So we take a small population, we do some modeling on it, some work on it, and then we can predict the general behavior of this data. Finally, graphical statistics provides us with visual insights into trends, outliers, or other relationships. Visual tools are the fastest way to explore a dataset. Civil engineers regularly use bar charts, pie charts, and histograms to see frequency distributions. We also use scatter plots a lot to check relationships. Another tool at our disposal is box plots, which helps us identify outliers and spread. For more complicated systems, we also use spider diagrams or dendrograms to compare multiple variables or groupings. Sometimes we fit a trend line to a scatter plot to uncover certain relationships. The R squared value that results from the plot tells us how well the line represents the data. R squared ranges from 0 to 1. The value that is closer to 1 means a very strong fit. But that's not always good, right? Something like 1 means that the algorithm or the line that we developed or the model that we've developed overlearned the problem. It didn't understand it, it memorized it. So whenever something new comes, it will not be able to deal with it. So I prefer something in the 92% range that shows understanding. Yes, it makes mistakes, but it also understands what's going on so that when something novel comes towards it, it is able to deal with it. And that's what we call a generalizable model, as in it applies for more than just its own situation. Now, switching to our numerical tools, we have the measures of central tendency, which are mean, median, mode. We have the measures of dispersion, how far things are, how chaotic my data set is, like standard deviation, relative standing, like percentiles, and measures of association, like correlation. Together, they help us understand both the typical behavior and how much variation in the data set to expect. So let's begin with central tendency. The mean is the average of the whole data set, the sum of everything over their number. The mode is the most repetitive or common value. The median is the middle value when the data is sorted. So, for example, in construction delays, we have a delay of 5 days, 8 days, 9 days, 12 days, and 15 days. They are mentioned in ascending order. So the ordering is done for us, right? So the median is 9. And that tells us the typical project delay time of this particular incident. Next, we have dispersion. Range is just the difference between the maximum and the minimum. So, what is the spread of the data set? Variance and standard deviation tells us how spread out the data is, like how chaotic, how things are jumping from the average and between each other. Coefficient of variation, or COV or CV, expresses the standard deviation as a percentage of the mean. The standard deviation as a percentage of the mean, and therefore it is unitless. A high dispersion may suggest inconsistent performance. So a high COV or CV might suggest inconsistent performance, which is a key red flag for us in engineering. In engineering, we like consistency. In other studies, that might not be the case. But for us in engineering, we like consistent behavior so that we can predict it and therefore design for it. Percentiles and quartiles show where a value lies relative to the rest of the dataset. If a bridge inspection gets a 90th percentile rating, that means it is better than 90% of similar bridges. These tools help us prioritize interventions. For example, focusing on the worst performing 10% of sewer lines. So we start with the ones performing the worst. To see how two variables relate, we use covariance and correlation. Covariance shows us the direction of a relationship, whereas correlation shows the strength of that relationship from a scale of -1 to +1. And that's a hint that correlation, small r, should never be outside -1 to +1. A positive correlation between vehicle loads and pavement cracking means if the vehicle is heavier, the heavier the vehicle load is, the higher the pavement cracking. So if one increases, the other one will increase. Whereas a negative relationship means if one increases, the other one will decrease. So to wrap up, statistics helps us engineers turn raw data into reliable decisions. We have graphical tools like histograms and scatter plots, and non-graphical tools like mean, standard deviation, correlation, R-squared, and so on and so forth. It is very important to understand the representation and the meaning of each one of them and how to use it. Thank you and take care.